In this lesson, we're going to look at the development of the periodic table. So we are familiar with the modern periodic table and all the information that it contains, but this is something that has been developed over the years. And the periodic table that we know originates from a periodic table put together by a Russian scientist, Dmitry Mendeleev, over 150 years ago. But before Mendeleev came up with his periodic table, there were a number of attempts to try and organize the known elements, most of them not particularly successful. It was only really Mendeleev that managed to sort of work out the pattern that fit all these elements together. But what we have here is a table developed by a British scientist called John Newlands, and this was a very close predecessor to Mendeleev's table. Now, you're not going to be expected to know any details about Newlands' table. You will, however, need to know details about Mendeleev's. But what can commonly be asked is for you to look at a copy of Newlands' table and make comparisons between that and the modern periodic table. So here we have a copy of Newlands' periodic table, and what I'd like you to do is to complete this double bubble map comparing this periodic table to the modern periodic table that we're familiar with now. So I'm going to start off with similarities. So first of all, we have rows and columns, which our periodic table has. Also, you'll notice that there are 1, 2, 3, 4, 5, 6, 7, 8 columns. And we know that there are 8 groups in the modern periodic table. Also, if you look at some of the elements, you'll start to recognize some of the pairings. Lithium, sodium, potassium. Well, those three are found together in the modern periodic table. So they are found together. And there are some other pairings. We also have fluorine and chlorine. They are also found together. So you'll find those elements together in both Newlands' periodic table and the modern periodic table. And there are a few others. Boron, carbon, nitrogen, oxygen, again, they're found together. Magnesium, calcium. So there are lots of similarities. But what is different? So the modern periodic table and Newlands' periodic table. So modern periodic table has more elements for starters. The modern periodic table has the metals and non-metals separated. And they are separated by the staircase. Newlands' periodic table, he has the metals and the non-metals mixed together. He also has fewer elements. So we're going to have fewer elements. Metals and non-metals were mixed together. Also, we've got multiple elements in the same box, which in the modern periodic table we don't. So we have more than one element in some spaces, or some places I should say. And we also don't, in the modern periodic table, we have groups and we have periods, which we don't have here. The modern periodic table, we also have the transition metals, or the transition block, which we don't have in Newlands' periodic table. So again, we've got plenty of similarities and differences here. So if you were ever asked to compare the two, we'd have plenty that we could, identify and write about. Now, like I said, you don't need to specifically know anything about Newlands' periodic table. If they ask you to make this comparison, they will give you a copy of his table. What we really need is our knowledge of the modern periodic table so that we can make that comparison. So the task we're going to do now is we're going to look at what Mendeleev used to organize his periodic table. Now, it's really important that you appreciate that when Mendeleev came up with this periodic table, he was very limited in what he actually knew about the elements. So we take for granted now that we know about the atomic structure, the protons, the neutrons, the electrons, the shells, the nucleus, and we have all of that information. And we know that our modern periodic table is arranged from left to right by increasing atomic number or increasing number of protons, and we know that they're arranged into groups based on how many outer shell electrons they have. But Mendeleev didn't have any of that information. He didn't know anything about protons, neutrons, or electrons. He didn't know anything about atomic structure. And also he was limited because they didn't have all of the elements. In Mendeleev's time there was only 63 known elements, and the modern periodic table has 118. So he was dealing with just over half of the elements, and he didn't know anything about their atomic structure, yet he was able to correctly put them into an ordered pattern, which eventually became the modern periodic table. So the information he did have was for the elements, they'd already been given chemical symbols and names. They'd had their atomic weight calculated. Now it's really important that if you're talking about this in terms of Mendeleev, it's not atomic mass, because we know atomic mass is the number of protons plus the number of neutrons. Mendeleev didn't know anything about atomic structure, but he did know the atomic weight of the known elements. Those 63 known elements, somebody else, another chemist, had calculated their atomic weight. He knew some of their physical properties, their appearances, their melting points, their boiling points, and their chemical properties, their reactivity. What other elements did they react with? What proportions did they react with, those other elements? And how vigorously did they react? So what Mendeleev did was he wrote down all of this information onto cards. So he'd have the chemical symbol, the atomic weight, and a list of their chemical and physical properties. And he used to try and organize them in such a way that he could try and make sense of those 63 elements and find the patterns that linked them. So that's precisely what you're going to do. A similar activity. I'm not going to give you 63 elements, but you're going to do a card sort activity where you have a variety of elements. Now these symbols, they're not actually, so that's not potassium. These are just random letters, okay? And the reason I've given you random letters is because it's really important that you don't just try and recreate the periodic table. So I've not given you actual elements, because otherwise you just look at the periodic table and put them into the right place without really having to work out why they go there. Now, you've got a simplified version of what Mendeleev had. He had much more information, but what you have is a chemical symbol, the mass or the atomic weight of that element, and how many oxygens or chlorines or hydrogens it combines with, so an idea of its sort of chemical reactivity. So what I'd like you to do is, once you've cut out all of your elements, there's also some gaps, okay? So you'll have to work out where they fit in. I want you to try and organize this into a periodic table. So looking at the elements that we have, the first thing that's logical is to look at their mass. So if we start arranging them by increasing mass from left to right, but we're going to have to think about something else, because otherwise we're just going to end up with a long line of elements. But we know their mass, so it seems logical that their mass would increase. But also, if we look at what they combine with, so their chemical reactivity. So this element F, it's got a mass of 1, and it combines with 0.5 oxygens. This element K has a mass of 7 and also combines with 0.5 oxygens. And then if I look at the next heaviest element, element R, mass 9, so it's heavier, but it combines with 1 oxygen, so that's different, but these two are the same. So instead of just making a long line, if they're the same, we're going to put them into a column. this one, R, is the next heaviest. It's not the same, so it's not going to go underneath, so we'll go next to it. Then the next heaviest, element B, has a mass of 11. Look at its chemical reactivity. Is it the same? No, so it's not going to go under, it's going to go next to it. Element J is the next heaviest. Again, that's not the same, so it's going to go next to it. Element S, again, doesn't match, so it's not going to go underneath, it's going to go next to it. Element G, again, doesn't match, so it's going to go next to it. Then the next element, element Q, is the next heaviest, but also 0.5 oxygens. Well, that's the same as these, so I'm going to put it underneath here. And then element P, well, that also reacts with 1 oxygen, which matches R. Element N matches 3 chlorines, so it matches with B. Element V, 2 oxygens, so that matches as well. Element D, 3 hydrogens, that matches. Element H, 2 hydrogens, that matches. Then element U, 0.5 oxygen, so again, that matches with these. So if you look at the columns, 0.5, 0.5, 0.5, 0.5, 1, 1, right? Their chemical reactivity is the same, but their mass is increasing, or their weight, I should say, is increasing as you go along. So element E, 1 oxygen, that matches. Element M, 3 chlorines or 1.5 oxygens, again, that matches. Then the next element, element A, doesn't match. 2 oxygens or 4 hydrogens, 2 oxygens, 3 hydrogens, so it doesn't match. However, it does match this one, so if we move it along one, then it does match. And this is precisely what Dmitry Mendeleev did. He took those elements and he arranged them from left to right by increasing atomic weight. And any time he saw similar chemical properties, such as the proportion they react with oxygen, he put them into columns based on those similar reactivity. But because obviously he didn't have all the elements, he wasn't going to be able to put them all in the right place. So when he came across the next heaviest known element and it didn't match, so here it does not match, he'd move it across until it did match. And what he then did was he'd leave a gap. And what he was saying was that there is an element that has not been discovered yet that is going to fit into that gap. And we're going to come back and talk about those in a little bit more depth in a minute. So then he took the next heaviest element, which in this case is I, which matches the reactivity of the other elements in that group. Then the next heaviest, T. So it doesn't match that group, it doesn't match this group, but it does match this one. So again, we've got a gap we're going to pop here. Next heaviest element, W, that matches 1.5 oxygens, 1.5 oxygens. Y, that matches 2 oxygens, 2 oxygens, 2 oxygens. And then finally O, doesn't match this group, but it does match this group. So again, we have a gap. Now, Mendeleev didn't just leave gaps for undiscovered elements. What he did was he predicted the properties that these elements would have. So he would look at the gap and he would say, okay, it's in between V and Y. Now every element in this group reacts with 2 oxygens. So he would predict that this unknown element would also react with 2 oxygens. He looked at the melting and boiling points of the element above and below and was able to predict what he thought the melting and boiling points would be for these undiscovered elements. And some of these elements were discovered many, many years, not only after he developed this periodic table, but years after his death. And these elements that were being discovered fit perfectly into these gaps that he'd left, and in some cases were incredibly close. Their properties were incredibly close to the ones that he predicted just using this method. And that led to his periodic table being accepted as the correct periodic table, because he'd been the first person who had discovered the order of the elements. So he'd arranged them from left to right by increasing atomic weight, but then he grouped them into columns by their similar chemical reactivity. And if an element didn't fit the pattern of reactivity for that group, he would move it across until it did, leave a gap, and predict the properties of the element that should go in there. And then many years later, when these new elements were being discovered, it was found that they fit perfectly into those gaps, and they had very similar properties to the ones that Mendeleev had predicted. So once you've finished with your card sort, if you just answer these questions about how did you arrange your elements into the periodic table, what were the positives, what were the limitations, and why do you think the periodic table is so important? So, when we organised our elements, how did we arrange them into the periodic table? So, we went from left to right by increasing mass, and then we grouped them into columns based on their chemical properties, and in particular we were looking at the proportions they reacted with oxygen. So I'm just going to put reactivity with oxygen. Okay, what were the positives of your periodic table? Well, we were able to organise the elements. So we were able to organise our elements, and there were patterns that fit all of them. Limitations. We had gaps, didn't we? We didn't have all the elements. Didn't have all the elements, therefore had gaps. And also, not that Mendeleev would have known it, but we didn't know anything about the atomic structure. We were organising them by mass, and we were organising them by reactivity with oxygen, but we didn't really know why. So we didn't know why the elements fit. So the actual periodic table is so important because it tells us everything. It tells us the atomic structure, it tells us if it's metallic or non-metallic, it tells us it's likely to be reactive, the compounds it's likely to form, the structure and bonding it's likely to have. It really is a wealth of information, and it's absolutely essential to chemistry. So it allows chemists to deduce atomic structure, it allows us to predict chemical and physical properties, and it allows us to predict structure and bonding. And that's just a summary. That the amount of information you can obtain from the periodic table really is immense. So, we're going to talk specifically about Mendeleev now. So, to arrange the elements from left to right in periods, Mendeleev organised them by increasing atomic weight. Okay, not mass, increasing atomic weight. And he organised them into groups by similar chemical properties. For example, reactivity. So what did Mendeleev do differently to previous attempts? He left gaps for undiscovered elements. He was the first person to suggest that there were many undiscovered elements. All the others, so Newland's table, you'll notice there was no gaps in Newland's table because he thought he had all the elements. Mendeleev left gaps for undiscovered elements. And leaving the gaps wasn't as significant as the fact that he also predicted the properties of these undiscovered elements. So he predicted, and I'm going to put in brackets, correctly, the properties of these elements. So, give 2 examples of things that Mendeleev did that led to his periodic table being accepted by the scientific community. So, number 1, he left gaps. If an element didn't fit the pattern of reactivity for its group. So if he was trying to put an element in and it didn't match the pattern of reactivity for that group, then he would move it along until it did. Okay, and he predicted properties of these undiscovered elements. And the other thing he did was he swapped some elements around. So a good example, if you look at the periodic table, is to look at tellurium. If you look at tellurium and iodine, and you look at the order that they're in, so if I just put the periodic table here, we look at tellurium and iodine. Tellurium has an atomic mass of 128, iodine is 127, which is, if you look at it, that's the wrong way round. You would have the smaller number first. The iodine should go before tellurium. So if Mendeleev was organising them by increasing weight, then he would have also put iodine before tellurium. But he didn't. He swapped them around. Even though he knew that tellurium was heavier than iodine, he put it before. Because if he'd put them the other way around and put iodine first, then tellurium, so iodine would have been in group 6, and iodine does not match the pattern of reactivity for group 6. Tellurium he would have put in group 7, and tellurium doesn't fit the pattern of reactivity for group 7. So he was so confident that he was right, that the elements had to be grouped by similar chemical properties, that he actually swapped tellurium and iodine around. And he put iodine in group 7 and tellurium in group 6 because that's where they matched. The tellurium did have the same properties as the other group 6 elements, and iodine did have the same properties as the other group 7 elements. So that is another thing that he did that led to his periodic table being accepted as the correct periodic table. So he swapped elements based on their atomic weights, so they matched the pattern of reactivity for their group. Example, tellurium and iodine. So to summarize, we're just going to make a flow map showing the process Mendeleev went through to produce his periodic table. So number 1, he organized the elements from left to right in periods based on increasing atomic weight. The second thing he did was he arranged the elements into groups based on similar chemical properties. For example, reactivity. And then importantly, if an element didn't fit the pattern of reactivity, for its group, he moved it until it did, and left gaps. And he didn't just leave gaps, he predicted the properties of these undiscovered elements. And again, years later, when these elements started being discovered, they fit perfectly into the gaps and they had the properties that he predicted. So, there is our flow map showing how Mendeleev developed his periodic table. So what I'd like you to do now is a double bubble map, this time comparing Mendeleev's periodic table to the modern periodic table. And we're just going to ignore that typo up here. I should say Mendeleev's. So Mendeleev's periodic table compared to the modern periodic table. So we're going to start with similarities. So we've got groups and periods. Both the modern periodic table and Mendeleev's have groups and periods. We have metals and non-metals are separate. We have patterns of reactivity in a group. So let's look at what's unique. So Mendeleev's periodic table, so from left to right in periods based on increasing atomic weight. Now the modern periodic table is arranged left to right in periods based on increasing atomic number or number of protons, which is something that Mendeleev didn't know about. And Mendeleev's are grouped by similar chemical properties. And the modern periodic table, they are grouped by number of outer shell electrons. Mendeleev's periodic table had gaps and 63 elements, whereas the modern periodic table has no gaps and 118 elements. So what we can see is Mendeleev, when he was grouping them by chemical properties, he'd sort of stumbled across the fact that they will have the same chemical properties, and we know that the modern periodic table, they're organized into groups because of the number of outer shell electrons. Well, it's because the number of outer shell electrons determines the chemical properties. So he didn't know anything about outer shell electrons or electrons at all, but he had stumbled across the pattern because it is the number of outer shell electrons that determines their chemical reactivity, which is why these elements he was putting into groups had the same chemical properties, because even though he didn't know it, he was grouping elements that had the same number of electrons in the outer shell. And again, if we look back at tellurium and iodine, now Mendeleev swapped them around. Now the reason why tellurium didn't fit in group 7 and iodine didn't fit in group 6 and he had to swap them around was because tellurium has 6 electrons in its outer shell, which is why it matches group 6 rather than group 7. And iodine had 7 electrons in its outer shell, which is why it matched the elements in group 7 and not group 6. And if you look at their atomic number, even though iodine is lighter, it's got a lighter mass than tellurium, it does actually have a higher atomic number. It has 1 more proton than tellurium. So in terms of atomic number, iodine should come after tellurium. So again, even though Mendeleev didn't know anything about atomic number or protons, he still got these elements in the correct place because he made sure they sat in a group with the same chemical reactivity. Even though he didn't know that that was due to outer shell electrons, he still got it right. So for the next 10 minutes, I'd like you to just complete this 10-mark facts test. So I'm just going to go through the answers quickly and make sure you're making your corrections in green pen. So how many electrons can go into the second and third shells? Each one of those can hold 8. How did Mendeleev organize his elements across his periodic table? It was increasing atomic weight. What name is given to a substance containing only one type of atom? It is an element. Name 2 features of the nuclear model. So you can have dense, positive nucleus, but you must also have electrons in orbitals or orbit around the nucleus. How many electrons are in the outer shell of phosphorus? So phosphorus is here, group 5, so 5 electrons in the outer shell. What is the electronic configuration for an atom of sulfur? So sulfur is in period 3, so it's going to have 3 shells, and it's in group 6. So it's going to have 6 in the outer shell, which means that the other shells must be full. So it's going to have 2 in the first shell, then 8, then 6, and if you just double check that all adds up, it'll equal 16, and the atomic number is 16. How many protons are in an ion of oxygen? Now, don't be thrown by the fact that it's an ion. They're asking for protons, which means it doesn't matter if it's an ion, doesn't matter if it's an isotope, doesn't matter if it's an atom. Every single atom, ion, or isotope of oxygen must have the same number of protons. Oxygen has an atomic number of 8. It must have 8 protons. The relative charge of an electron, -1. What is an isotope? So this is a very specific definition. Make sure you've got this down. So they are atoms of an element with the same number of protons but a different number of neutrons. You need all three of those to get the mark. Atoms of an element with the same number of protons but a different number of neutrons. And finally, how many electrons are in an aluminium ion? So, aluminium has 13 electrons to start with. Okay, it's a metal, so it's going to lose electrons, and metals lose however many they have in their outer shell. Aluminium is in group 3, so it's got 3 in the outer shell. So 13 minus 3 equals 10.